To analyze the motion of the system, we start with the force from the spring. If we assume the ideal spring, we will assume that the spring follow perfectly the Hooke's law. That is, the force from the spring Fs is equal to the minus kx. Here we will use the notation of the one-dimensional vector. That is, I will represent the vector as the algebraic number of the force and use the sign as the direction, because the force here we talk about the force from the spring, which is the one-dimensional force. This F equal to minus kx, it means that if you have an object attached to a spring and at an instant of time the object is at position x from the equilibrium position, we say that the force from the spring F is equal to the minus kx. So x is the position of the object from the equilibrium point. Here we define the positive x to the right of the equilibrium point, and the negative x is to the left of the equilibrium point. The negative sign here tells us that the force from the spring will point in the opposite direction to the direction of x. So in this situation, the object is here and x is positive, so the force is negative in the sense that it points in the opposite direction to x. So this is the force for the object attached to a spring. Again, remember here that first, for the simple system, we will ignore, or we will assume that there is no friction. There is no friction between the object and the horizontal surface. So the net force is the force from the spring only, and this is a Hooke's law. From the Newton's second law, we can see that this Fs equal to the minus kx can be written as is equal to the ma, okay, or it's equal to the m d square x by dt square. So we can write the equation of motion as the d square x by dt square is equal to the minus of k over m x. And if we define the quantity omega as k over m, we will have that the equation of motion is d square x by dt square is equal to the minus of omega, if we define this as omega square is equal to the k over m, so this equal to the d square x by dt square is equal to the minus of omega square x. And this is the equation of motion that we have to solve to get x as a function of t. Okay. In general, we can solve this equation using the knowledge of the differential equation. But here, I will not do that. I will not show you the detail of solving this equation using the differential equation, solving this differential equation directly. But I will give you the solution and show you that it's valid. The solution of the equation of motion x as a function of time t is a cos omega t plus phi. This is one of the solution. It's not only the solution, but it is one of the solution of the equation of motion. We can see that this xt is the equation of motion easily. We can do this by first, if I calculate the first derivative of xt, so we have that dx by dt is equal to the derivative of the right side. Here we define this a as a constant. We will discuss the meaning, the physical meaning of a later. Also, omega is a constant and phi is a constant. So I will write it here, a omega and phi is a constant. So when we do the derivative here, we can take a out of the process of derivative. So we have this equal to a d by dt of cos omega t plus phi. The derivative of cos function is a sine function, right? It's a minus of sine function. So this is equal to a minus of a sine omega t plus phi, and we have d over dt of omega t plus phi. And as we have defined that omega and phi are constant, so the last derivative will give us the omega. So we have that the first derivative of x with respect to t is equal to the minus of omega a sine omega t plus phi. Okay, so this is the first derivative of the x with respect to time t. Next, we will do the second derivative. For the second derivative, d square x by dt square is equal to the d by dt of dx by dt. So it's equal to the d by dt of the minus of omega t, of omega a cos omega t plus phi. Okay, so we can do this again using the condition that omega is a constant, a is a constant, and phi is a constant. At the end, you can do this, it is very easy, but at the end we will have that the derivative is equal to the minus of omega square a sine omega t plus phi. Okay, but we know that a sine omega t plus phi is x. So what we have is that the second derivative of x as a function of t is equal to the minus of omega square x. And this is the equation of motion of our problem. So it means that x, this x equal to a cos omega t plus phi is the solution of our problem. Dx by dt equal to d square x by dt square is equal to the minus of omega square x, which is the second law of motion of our problem.